Stan has an interesting personal story that I thought I would share with you. Now, I did what all of you do in such a circumstance. I went to the web, and so the province of this statement is a little suspect. Let me just read it. Ranked second in his high school class, he dreamed of studying physics in college. But despite his mother's best efforts, Stan lacked the necessary resident status to qualify for federally funded financial aid. I was devastated, says Stan, then an undocumented immigrant from El Salvador who has lived in the United States since he was 7. For 2 years, he studied calculus, physics, and chemistry on his own while his case was appealed to the INS. Did you say you were washing dishes during this time?
I could have been.
Yeah, okay. Think about that, guys. Okay. After much hard work, he finally straightened out his paperwork and sent in his college application. Stan chose Oxy over UCLA and UC Berkeley. And then there's some sort of nice things that it says about Oxy. Stan made the most of his experience by collaborating with me to research dark matter, with some advanced level courses enrolling. Stan is on track for reaching the stars. Okay, so Stan was in our 3-2 program, so he went to Caltech, and there graduated in 2 years. But in the summer, unfortunately for the dark matter field, he switched to a new field, which is plasmonic research. And then after he graduated from the 3-2 program, he entered the graduate program there and has 1 more year to go until he finishes this. And today, he's going to talk about plasmonic metamaterials. So let's give a warm welcome for Stan Burgos.
All right, great. Thank you, Dan. That was a very nice introduction, and I think sums everything up from when I started my academic career to where I am now. Let me just say, it is a great honor to be back here in my alma mater, despite I went to Caltech. This is still where my heart is. But in order to understand metamaterials, we first have to understand, like, what is it that nature gives us to work with. And in the most basic sense, once you're given a material, whether it is, I'm sorry, I skipped a couple of slides there. I saw the answer already. Well, anyways, so if you're given a material, say a piece of glass, piece of silicon, and I ask you, if I send in electromagnetic radiation down, at an angle, how does it interact with that material? Well, we know from electrostatics and electrodynamics that the response of the material is going to be dependent on how well the atoms polarize and how they magnetize once you put them under an electromagnetic field, right? So this is standard E&M stuff. Griffiths does a really great job, and I love that book. And then you find that if you go through the electric susceptibility of the material, you find that the atom polarizability here, P, is going to be proportional to the electric field in the direction in which it is. So the susceptibility ends up always being greater than 0, meaning that the relative permittivity is going to be greater than 0, right? So that means that the relative permittivity is either 1 or greater than 1, 1 being where it is in vacuum. For the magnetic susceptibility, it's a little bit different. Essentially, once you apply a magnetic field H, it tells you how well the magnetic moment of the atoms align, either parallel or anti-parallel to that incident H field. And whether you have an even or odd number of electrons orbiting the atom, you find that it's either parallel or anti-parallel to this H field. But regardless of what it does, it turns out that if you take the ratio of the polarizability of the electric field and the susceptibility of the H field, that ratio ends up being very small, just on order of magnitude. And I think, again, Griffiths has a very nice example of that. And it just comes down to the fact that H field is E over C of the electric field. So it's just that much lower, so it's not going to have such a huge effect. So what ends up happening is that you end up having susceptibility in the magnetic field that's approximately 0, right? So what that means is that you get the relative permittivity is greater than or equal to 1, and the permeability is approximately equal to 1. That's why once we calculate the index of a material, we never really care about what the permeability is. We just take it to be 1, right? And this is something that pretty much standard in all textbooks. Nobody argues this. And then you find that the index of that structure is, in its full form, is the square root of epsilon plus mu, times mu. But mu is approximately equal to 1, so you just the square root of epsilon r, which is greater than or equal to 1. So now, if I send in an electromagnetic wave into a medium, the way that it behaves inside of this medium is going to depend on this index pretty much. If it comes in at some angle of incidence, first off, you know that the K vector coming in is going to experience either a stretch or contraction based on the index of the material. Well, because the index is greater than 1, and you're dividing K naught by n, this is just the effective K vector inside the material, which tells you the wavelength in the material. You're going to find that K vector is going to be between 0 and K naught. So essentially, it's going to shrink inside the wavelength. That's why you have wavelengths that are effectively shorter inside of a material, right? Furthermore, from Snell's law, which is, essentially, if you follow if you guys have taken Lagrange mechanics, you find that if you propagate a beam through some inhomogeneous medium, it's going to follow the path of least action, and that's where this comes from. Essentially, it tells you where the beam is going to deflect. So this is elementary stuff. I haven't really said anything that's not outside of your undergraduate education. But then, very, very straightforwardly, you find that if you follow these dynamics, you get nothing too surprising, but which is that so here the direction of the arrow represents the direction of the phase, and the deflection of the arrow, whether it's up or down, depends if the energy is refracting as we expected following Snell's law, and if it follows back here, it would be negative, right? So far, I'm just recapping classical dielectric materials, right? So another way that you can think of these is if you look at metal optics, right? So metal optics behave differently because whereas the dielectric constants are actually related by an electron that's bound about an atom. In this case, for metal optics, you actually have one core, and it actually releases 1 electron per core roughly, and that gives you a sea of electrons, right? And at visible frequencies, you can actually approximate this by a grid of positive cores in the material, and then if you put an electron, if you can imagine each atom donates 1 electron to the material. You apply an electric field, but what's going to happen is that it's going to scatter, within these core centers in the material. And you can actually write the dynamics for this. So, in this case, the electron accelerates, then, it scatters, it moves some other place, it scatters, and so forth. And then there's a correlation time, as to how often this happens on average, and that's called the collision time. And again, we can just go back to our textbook equations, and we can say that the change in momentum is going to be related to how much force is applied by the electric field, and also this restoring force that kind of changes the momentum as it collides, and that's related to the collision time of the electron. This is called the Drude model, for those of you who haven't seen it. But if you follow this through, you actually end up with another expression for the relative permittivity. And that tells you that it goes like 1 minus the plasma frequency over the frequency of operation. The plasma frequency simply tells you if you have an electron gas, you can imagine positive and negative charge propagating down the film once you apply an electric field. And this is what gives you this equation, and if you are a plasma frequency below a frequency below the surface plasma frequency, you're going to find that the relative permittivity is negative. So if the permittivity is negative, I just showed you that mu has to be 1, right? Because the material is actually, okay, by the way, we're not talking about extreme materials like high electric field and magnetism, as Professor George Nushoff can attest to. I'm talking about regular, piece of wood, a piece of glass, like these sort of things that we experience on everyday life. And what happens in this case is that, the index actually becomes imaginary, right? So the index tells us how well the propagation vector is going to change inside of the material. And in this case, what's going to happen if you have an imaginary index is that you're going to have an evanescent tail inside of the material depending on which frequency you're working at. And then, most of it, because of conservation of energy, that energy has to be reflected back, right? So, any questions thus far? Right? So far, so good. Okay. Well, I explored epsilon and mu for regular materials, and I showed you that positive index materials, isotropic dielectrics, for example, follow this relation. Epsilon and mu is greater than 0. Well, mu is actually equal to 1, and this could be greater than or equal to 1. So then, if you take the index of this material, it'll just be the positive of those. So again, this is the range what we're interested in. We're not interested in, but rather used to, right? Nature around us gives us this by default. I also showed you that if you excite with a given angle of incidence, there should have been a color here that separates it. But anyhow, you can imagine that there's an interface, and then it refracts with a positive angle, and phase moves away from the interface. I also showed you that for the case of metals, mu is actually equal to 1, and the permittivity is less than 0. And this gives you an index that's imaginary. And like I said before, this actually leads to something that decays evanescently in the metal, but it actually reflects off of the surface. There's another interesting part which has to do with magnetics. And here you can actually, if you apply a strong enough magnetic field to atoms that have an odd number of electrons inside in the deep core of the atom, then you can get a negative permeability in these cases. But again, if epsilon is greater than 0 and mu is less than 0, you again are going to be left with this index that is in the imaginary regime. And again, you're going to have something that reflects up from the interface of the material, right? So now the interesting part that I want to focus on today, and actually there's a lot to explore within this parameter space. But the one that's most interesting, or not most, but the one that got the most attention back in 1999 was negative index materials that are not naturally occurring, but that we can tune based on meta-atoms, which I'll talk to in a bit. And then, in this case, the relative permittivity and permeability are both less than 0. And you can show that if this is the case, you actually get an index value that is real and negative. Okay, so that is something that we do not experience in nature, right? Okay. So, what does it mean to have a negative index material? Well, like I told you before, the index is going to be the negative of it's going to be the root of the negative permittivity and permeability. You can factor out the negative, the root of negative 1, you get a nice square, you get a negative, and so the index is negative. There's an argument here if you're just follow. I mean, if I were given this equation, I'd say, well, negative is positive, and well, why am I even bothering with this? It turns out that this is a simplified model because whenever you deal with the index of a material, it comes with a lossy part. For simplicity, I'm assuming that everything is real in this case. But there's actually, the permittivity and the permeability are actually complex. So there's an imaginary part that I'm ignoring. And if you write the whole thing out, then it turns out that you have to, if you take the square root of a complex number, you have 2 Riemann sheets pretty much, right? And in order to be consistent with energy laws as you propagate, you have to pick the negative branch. And that's what leads to this. So that's where this comes from, but it's consistent. Just for simplicity, let's assume that this is way it looks. So now, as we go, if it was a positive index material I showed you, it should have refracted like with a positive angle, face moving forward. But because the index is negative, we know that the k vector inside the material, by the way, k vector is nothing more than saying what is the wavelength of the material, right? So k is 2 pi over lambda. It tells me how much the wave shrank, and by white and by what number. So in this case, the wave vector inside the material is going to be normalized by negative n. So now this is interesting because whereas before the k vector actually just shrank, it's not only going to shrink in this case, but it's actually going to have a negative value. And what does that mean, right? Well, k, if you think about it, relates to the phase of the material. So this is going to correspond to negative phase propagation. Okay, and I have some cool movies later on to show you what that means. Similarly, if you just do basic Snell's law, I mean, what's really cool about this is that if you follow the equations I'm writing, there's nothing complicated here. It's just saying what if it was negative, and you can just back out all the effects of this, right? So in this case, if n was negative, then you would get a negative refraction angle. And to do this really fully, you have to imagine the full energy density propagating through a medium and how much is going into heating the material and so forth. So that is the full way to do it. This is the easy way. Just look at Snell's law and it gives you actually the same answer. So, and then what happens in this case is that you get an angle that's negative, so it refracts to the same side as the incident angle. And furthermore, the k vector actually propagates backwards, right? So that's counterintuitive. This is not something that we see in everyday life. So here's a quick simulation of what this would look like, right? So we have n equals 1, so this is just vacuum in here. This is obviously an artificial material. We can just take FDTD simulations, which simulate Maxwell's equations in its entirety, and then we see what happens as we excite it. So what's going to happen here is we excite a Gaussian beam. It comes into contact at this interface, and then it goes into the -1 regime. So what you can see, first off, is that it refracts to the same side that you excited. Second, the thing to notice is that face front actually moves backwards, like I told you it would, right? And once it reaches the next interface, now you again have positive refraction with face fronts moving forward in time, right? So this may seem like hocus pocus and I'm just making stuff up, but this is actually something that is not prohibited by Maxwell's equations. The only reason why we haven't observed this is because we always take real materials such that the permeability is equal to 1, right? Metals, I told you, gives us permittivity -1, but now if we can somehow tune this, then we were able to access these exotic behaviors. And there's a lot of implications on this. I mean, you can get stuff like superlensing, which I'll touch on later. And I mean, okay, from an academic standpoint, this is just cool. Okay, but people in industry or like the military want to know, well, can you actually do something cool to hide my tank or something like this? And again, I'm just drawing here the pointing vectors showing again that you refract negative and then negative with the phase front moving back. So that is a simulation at a single frequency. The interesting thing to note is like what would happen if we had a broadband negative index material, right? So this is a very, I don't know if you guys have seen this before, but this is a straw in a glass filled with air, so n is equal to 1. If we were to fill this with an index of 1.3, wherever it is, Kool-Aid, whatever you guys drink, so then you would get, something that actually, because the index is greater, it would actually deflect towards the normal, right, of the interface. The cool thing is, what would happen if you have a negative index, Kool-Aid, for example. By the way, I'm not getting commission off of Kool-Aid, I'm just using that as an example. What's interesting is that you actually get this negative refraction within that liquid. And then another interesting to note is that whereas before, for the positive index case, you cannot see the surface at the bottom of the glass. In this case, you actually are able to peek around the glass and see the surface from underneath. you do not need to worry what this might taste like because this is only a simulation. And we actually, we use Povray, which is a really popular ray tracing tool for doing these sort of things. But how could we actually obtain such materials? You know, they're interesting, as I showed you. You know, they do cool stuff, but like, you know, what can we actually do with these? So it took the genius of this guy Henry, who's done a lot of, you know, interesting stuff in a lot of the fields. And then he said, well, you know, we have these bulks of glass or whatever material you have, and then you have these meta-atoms. I'm sorry, you have these atoms. You know, like I told you, they become polarized, they have susceptibility that's magnetic and electric, and that gives you the index, and the index ends up being roughly positive, right? But what if we could make artificial atoms, which he called meta-atoms? Meta means beyond what we know, right? If we could actually create these meta-atoms, what could we actually realize with these? So then what he came up with was this thing called the split ring resonator, which some of you might have heard. But essentially what it does is that, you know, you're excited with the magnetic field that's in this direction, E, H, and K. And then what happens is that the magnetic field actually goes in and out of the board in this case. So you can imagine, because of induction, it's actually going to oppose or go with the magnetic field frequency. But if you actually make it such that you have, actually the first way this was done was like to have a closed ring. But it turned out that the resonance was so weak you couldn't detect it. So what Pendry did is he just said, you know what, let's just cut a slit in it and make it an LC element. And in this case, you find that you have a very sharp resonance at a location that's consistent with the 1 over LC. So essentially he used transmission line theory to describe these using LC elements. And indeed, if you find, so essentially the way you think about this is that, you know, it's driving us at some frequency, but when the actual element is in resonance, you actually, the element actually opposes the field. So actually your pi phase shifter from the way it's driving in, the way the element is responding, right? So you actually get a diamagnetic response in that manner. And then here is one of his original calculations in top of the black and white plot that, you know, he found that you get that resonance, this would be the omega naught, and you get that the real part of the permeability actually dips below 0, right? So the disadvantage of this is that it only works for a certain bandwidth. It's not a broadband. Okay, fine, but it's a starting point. And actually, there's a lot of research going on right now as to how we can make this broadband for useful applications. But what he did was this. And then David Smith, I didn't write him here, but actually he worked closely with him. He took these meta-atoms and then he made printed boards of them. So he just took printed boards. These are actually, like each element's about millimeter thick. And I think if I were to draw a length scale here, it's about an inch or so. So they're big, you know. Okay, but it's useful, but you know, like in the realm of optics, and you know, actually the military was interested in this because you know they deal with these long wavelengths. But for us, if you want to see like that cup, you know, with a negative refraction, you want to actually bring this down to smaller wavelengths. Nevertheless, this was the very first implementation that was done in 2001. And then what they did was they made a wedge such that these had the positive permeability. You saw that it had a resonance, so it has a positive and negative index part. So if you make the positive index part, you find that you actually have regular refraction. So you know, you refract to the opposite side of the surface normal. But then he showed that if you actually hit it at a different frequency, the frequency that corresponds to the negative permeability, you actually are able to refract to the other side of the surface normal, right? And here's just what that looks like, which is, it's interesting. At first it was really bizarre, and actually there was like a 5 to 6 year battle between David Smith and his competitor saying that yes, it works and no, it doesn't, and you know. But at the end, it turned out to be correct. But so don't be afraid to claim things that don't seem obvious at the time. You know, in the end, if you win, then you're in good shape. So the other thing is that I told you this started off, you know, back in 2000 with these, you know, this is 3 millimeter length scale. So they're huge, and you know, these guys were doing, you know, these huge microwave experiments. But then because people like to, crowd things into the optic, and, for several reasons, right? You can imagine bringing this technology into, like, photonic chips and, integrating with electronics, so that can be very useful. So in that case, you can see that as time progressed, this is a bit outdated, but as time progressed, people very quickly crowded into the visible, right? And it turned out that the resonance, because it is a resonance loop, remember I showed you that split ring resonator, as you go into visible frequencies, the properties of the metal change, and then it's able to scatter less and less as you go into the visible frequencies. So you're actually dominated more by loss in this case, and you cannot access, I think the highest, the shortest wavelength they can do is about 800 nanometers, which is still close enough within the visible range, but not really quite where we want it to be. So then this led several researchers, and I think our lab was one of the first to recognize this, was that we could actually use these things called surface plasmons. So I'm going to now introduce a new concept, which is surface plasmons. And these are essentially E&M waves coupled at a metal dielectric interface. It's nothing more than an E&M space. You have a metal, and I told you metals, they can be excited, or they can be modeled rather by these plasma oscillations of electrons. If you bring them close together, they're going to be able to couple, okay? And then the solution for these coupled waves actually decay in the X direction in both cases. And if you actually plot like a charge density at the surface as plus minus, you get like the electric field in the X direction might look something like this, and something like this in the bottom. Okay. I mean, this is not very difficult. There's tons of literature how to do this. It's almost standard textbook stuff. You find that you get this type of distribution. The beta is the direction of propagation, and the HY is out of the board. So it's actually a TM wave, right, which doesn't have any component in the direction of propagation. And there's an E field that mostly points in the X direction. What's interesting about this, and which alludes to the part of the negative index, is that if you look at if you use the Ranham rule, I'll never forget that. If you use E cross H at the dielectric interface, you get energy pointing to the right, which is the direction of beta. But if you do the same, there's actually discontinuity here in the E field because of the charge distribution. It's going to point in the bottom, right? So the E is going to go to the bottom. So you get E cross H is going to point in the backwards direction, right? So now you're going to have something that is forward goes backwards, so you end up having a slow wave. And so the phase advance actually moves a lot slower than it would in free space. Okay. And this is just what I just said. There's an exponential decay going up, and there's the oscillatory solution going in the Z direction. And to show you how this works, let me just show you. I mean, I think pictures are worth what's called 1,000 words, and imagine a movie even more so, right? So then, this is the dispersion relation if I take silver and silicon. Remember I showed you the two interfaces. I have silicon and I have silver, and see how that behaves. Well, the dispersion relation looks something like this. Have you guys seen dispersion relations? You guys are familiar with what that means? So all it means is that if you take a given frequency, okay, so first off, take the light line. What I'm drawing here is the light line. It tells me that if I pick a frequency and I can take the wave vector, and omega equals ck, right? So given the frequency, and knowing the velocity, then I can tell you the wave vector. So just omega equals ck. It's nothing more than that. But in linear media, it looks like this. That's what we're used to. You guys see those cones and in XY space. This is exactly that, except that now we have coupled waves which couple at the interface. So now, and I told you they become slower as you couple into the radiation and into the surface plasmon mode. So it actually brings the K vector further out from the light line. Okay, is that clear to everybody? So it actually makes the K vector longer, which means the wave becomes shorter. I hope that's clear to everybody. If not, talk to me after. I can explain it in more clear detail. But then it turns out that whatever is to the left of the light line is called the radiation mode, because these are the wave vectors that. So these are the if I have omega k, right? Everybody has seen this, right? So the slope gives you the velocity of the light. But it turns out that anything to the left of this, you can excite, because you can have any number of k vectors that excite this type of dispersion relation. And so that's why everything to the left is called the radiation mode, and everything to the right is called the bound mode. The bound modes are the other surface plasmons, okay? And here, just let me show you, if I excite something at, at 300 nanometers, it looks something like this, okay? And if I launch that surface plasmon, remember the surface plasmon has this peak intensity at the interface. It's kind of choppy, but the point is that it's not sticking to the surface, it's actually radiating, and that's what that means by radiation mode. So this is not the solution we want. If you want to actually make something that's bound to the surface, make an optical circuit or something like that, then you're actually going to need not this type of solution. So actually the modes that we care about, that's just the time average field along the interface. Then what we're going to want is actually to work with higher k vectors, right? And the higher k vectors are actually going to be bound to the interface. You can see that here, that they actually don't radiate to space. The only radiation that you have is that you have an exponential decay above and below the metal interface. Okay. And here I'm showing that there's actually, that they're bound and that there's a, what I didn't mention before, that there's also a decay because there's ohmic loss. You can imagine you're sloshing electrons and you're actually suppressing that. Okay. So that's that. Okay, so now the next step is like, I found that I can kind of get energy to move backwards, but now the real way to do it is to actually sandwich two MIM configurations, drop them on top of each other, and then intuitively you might think you can get symmetric and anti-symmetric configurations. Imagine two plus charges, a plus and a minus charge, right? And then in this case you're going to get something that looks like this, just as I showed you before on the field profile. And in this one, it would be something that would look anti-symmetric, right? This is intuition, so always believe your intuition, I guess, is the moral here. Because once you solve Maxwell's equations, you exactly get that solution. You get symmetric and anti-symmetric solutions. But, we knew that already just by looking at the symmetry of the problem. Solutions have this form here, not so important, but what is important is that now we have two types of modes. So again, dispersion relation tells you for a given frequency what wave vector you're able to access, right? And the wave vector tells you the phase, right? So whereas before we were only cared about positive k-space, if you make this thin enough, maybe below 40 nanometers, you're actually able to access negative k vectors. Now what does that mean, right? So negative k vectors, I told you, corresponded to negative phase velocity, right? So, okay, so let's see, let's do this carefully. This is kind of an important point, so any questions? I'll ask somebody to explain it back to me just to make sure people know. So you have, so I call this the symmetric mode, right? The symmetric mode, just remember omega k just tells me the velocity and the energy propagation of the wave. So if I excite this mode, you get this type of dispersion, and you see this is beta, which is the propagation vector. This is a real part, so it's positive. That means that I have positive phase advance along that direction. If I excite this anti-symmetric mode, now that lives to the negative side of zero in k-space, which is interesting. Why haven't we seen that before? Well, part of it is because when people calculate these, they just cut it off at zero. They're like, well, what's going to happen back there? It's just going to be an evanescent mode, right? But it turns out that it kind of is that actually. It's actually a decaying mode that samples more of the metal, and that's why it acquires a negative k component in the phase. So now, let me see what's the next slide. Maybe I should just go there before I go here too long. Okay. So I told you we have negative mode and positive mode. Okay. So which one do we actually couple into, right? So we know that like the direction of propagation, like the k vector, right, is going to have a positive part, a real part and imaginary part. Imaginary tells me how much it decays as it propagates, right? So if I excite something above this line, right, I'm going to, let's say, the one that's going to be excited is the one with the lowest loss. So I think this has loss, this is phase. So this has the lowest loss, meaning that I'm going to excite this mode. If I go below here, the red curve has the lowest loss, I'm going to excite the positive index mode, right? That's pretty self-explanatory. So now, what I told you was that if I excite the positive index mode, right, because it has the lowest loss, it's going to have this type of symmetric profile, right? And if I excite above this, it's called the surface plasmon resonance. It's not important for this discussion. Then this has the lowest loss, so I excite this negative index mode, right? And that one has an antisymmetric profile. So let me first show you a movie of what it looks like. So it didn't really come out, but there's actually like 3 layers here: metal, dielectric, metal. It'll become obvious now that I'm going to send in a mode going in the forward direction. Choppy, and then it gets good, I think. Okay, there. So now you can see that actually the phase fronts move forwards in time concurrently with the direction of the pointing vector, which is the direction I'm sending it in, right? Now what happens in this case, right? So now I have the antisymmetric mode, and I'm going to again excite it with pointing vector going in the z direction. And in this case, forget that, that is numerics. Then in this case, you find that, okay, there it is. So now you find that the phase fronts again move backwards in time, right? And I mean, it tripped me up like the first couple of times I saw it, and I double checked, and it just works. And the reason it works actually, if you notice the mode profile, here it is very confined to the MIM configuration. In this case, it's very delocalized. So it's almost like a modem cutoff. And it is because it samples so much of the metal that you can get some of that backwards pointing vector contribution. Okay. So negative index in 2D. Okay, so I showed you that some of the samples or some of the things people could do with a negative index. And this is just the plot I showed you before. There was a theoretical paper in 2008 where they actually showed an MIM configuration. They excited at an angle, and they again observed that you have a negative refraction. And if you were to play the movie for this time snapshot, you see the phase fronts again move backwards in time. Not too important for this, but let me just mention that if you actually integrate the effective parameters along the thickness of the waveguide, you actually get permeability and permittivity that are actually negative. So it's consistent with the effective negative index mode of the structure. And perhaps the most critical part of here, there was a nice science paper that came from our group where they created a two-dimensional, so you can imagine you take this wedge, you take this slab, you cut it into a wedge, and then you send in light in one direction. It's really hard to see here, but if you excite with the negative index mode, you refract negatively, and if you excite with the positive index mode, you refract positively. So this was actually the first demonstration of bringing negative index technology down to the visible. Because like I told you, before that it was gigahertz, and it kind of saturated, like about 1 micron. But this was actually done, let's see here, I don't have the numbers, but this is actually a visible wavelength, 600 nanometers, for example, something you can actually detect with the naked eye. So now, that's kind of everything plasmonics, metamaterials. And what we did in 2010 was we took the same geometry of MIM waveguide, which I showed you. If you have an MIM waveguide, you make it thin enough, you can access the negative index mode, right? So we took the same geometry, and then we found the dispersion relation of that, metal dielectric metal. And then, not surprisingly, we found the same geometry. We have a negative index mode and a positive index mode. And again, the one you actually couple into has to do with which one has the lowest loss. So this one had the lowest loss, and we couple to this one, which is the one that's delocalized. By the way, delocalized, I mean that the mode is very leaky into the metal, right, which allows it to have that negative power flow. And then for the positive index mode, you can see the distinction here very clearly, by the way, because in this case, it's very confined to the inner core, so it's actually sampling more of the dielectric, so it's actually more forward propagating than backward propagating, right? And here, I can just, calculate what's the effective index using this very simple relation, and again, you find that these are indeed negative index modes and positive index modes, depending on which one you're exciting. But what's very interesting is that, I didn't mention this before, but like with the split ring resonators, people could get a figure of merit, which is defined as how much the real part of the propagation vector is compared to the imaginary part. So it kind of tells you how many oscillations you can get into your system before it decays, right? And in this case, I think the best metamaterial at 800 nanometers using split ring resonator had a figure of merit of 0.5, okay? Here we have a figure of merit of 10, so we can actually get substantial propagation into that material before it actually becomes useless, right? And this is our device. So what we did is we actually had an array of these coaxial structures. Incidentally, if you think about the symmetry of the coax itself, it's actually insensitive to angle of incidence, because no matter how you excite it, you always excite the proper negative index mode. And that is not necessarily the case once you have MIM configuration, right? Because for the MIM configuration, you actually have something that looks like this, right? You have a metal, dielectric metal. And I told you that the mode had to be TM. So you could only excite it with this polarization, right? Because you have the E field here, and then you have your H field here. This is the only way you can excite that MIN configuration. So by doing the very simple thing of wrapping this on itself, you actually gain a whole lot, right? And now you can actually excite this from free space and couple it into these models. I'm not going to talk about that too much right now. But it turns out that the spacing here is kind of critical, because you're actually coupling these because of the delocalized nature of the core. Remember I showed you that actually a lot of the energy leaks into the metal, and that allows you to have very strong coupling between these coaxial structures. So I can talk about that later if you guys like. Band structure, let's see, running out of time. I won't talk about the band structure, but it works. But what's interesting here is that so we verified all this using band structure calculations, so full field simulations, and we found that it works. What I'm going to show you here is that it's a full 3D simulation. I'm taking a cross section across this direction, and I'm going to excite the structure at an angle of 30 degrees with 483 nanometer. Remember, people have been stuck at 800 nanometers. We were able to skip the trouble from here and actually jumped into the blue. We're actually working from the blue down, right? So that's a really big advantage in these configurations. And if this works, as I come in, you see that after a transient, you actually, again, are able to form these negative phase fronts across the structure. And as these structures, as these phase fronts move, you can actually see that if you draw lines across here, you can actually see that the refraction angle is actually to the same side as you excited, right? So, yeah, okay, so that's kind of cool. If we take a time snapshot of this, and we integrate the pointing vector and the K vector, so the K vector we can just get directly from the phase fronts, right? So we get that the decay is actually refracts negative to the same side as the incident angle. The group velocity is a little bit. Is that something?
No, sorry.
Okay. For the group velocity, it's actually a little bit more complicated, because the pointing vector is doing like really crazy things in the end plane, right? You have you have to take E cross H throughout a unit cell, and it's not homogeneous. But if you average those out, you end up with a pointing vector that looks like this. So it has a component in the negative direction and the down Z direction. If you combine them, you get this pointing vector. So you can see that they're actually anti-parallel for this case, which is another thing, because a lot of people have been using photonic crystals just to use negative refraction, but not negative index, right? So essentially, in their case, they were able to refract to this side, but then the phase fronts still move to the forward in time. Okay, so that was different. So this is like a key result proving that we have a true negative index material. The other very cool thing, which I wasn't really clear on when I introduced the split ring resonator, was that if you have the split ring resonator, right? So I showed you it was something like this, right? And then you needed to have, once you excite it, you need to have E field going in and out of the board, right? So what that means is that if you actually turn the split ring resonator to any direction, it's not going to work. It only, if I put it this direction, it's not going to excite that resonance. It only works because it needs to be, having an induction in the end plane of this resonator. So that's another big limitation of the split ring. And what we show here is that because of the coupling between these waveguides and the negative index that we have already inherently in the z direction, we're actually able to have broad angle response. So which is the first demonstration of this actually in the field. So we're actually able to, at 30 degrees is the one I showed you before. If I go to 10 degrees, you can see that the phase fronts and the pointing vector actually shift consistent with the same index that we can calculate before. And if we go even to higher angles, you can see that the phase fronts actually change again with the pointing vector and is all consistent with an index of about -2.4. So this was actually the first isotropic, or broad angle rather, metamaterial to work at visible frequencies in the field. And we took a little bit of heat when we got this out, but hopefully we was shushed them some more because we're actually fabricating this, and hopefully that'll quiet that out. So another thing is actually, okay, so we have infinite slab, right? But how do we actually use this, for example, in experiment, right? So the easiest thing to do in an experiment is to actually cut a wedge out of it, right? Because the refraction angle will tell you what is the index that you're actually probing. And then this is another full field simulation where I'm exciting a wedge of 3 degrees, and I'm checking the direction of propagation. And what's very interesting here is that you can see the index, the phase fronts moving forwards as you enter the slab, they're moving backwards inside the slab, and that negative phase gradient across the wedge is actually causes a negative refraction at the output of this material. You might argue that there's only a near field effect. What happens if I'm standing, centimeters away or a meter away? Would I actually see that? But this is actually what we're doing here. We actually take the near field, project it into the far field, and we can see that we get a refraction angle from this wedge that's consistent with the index that we expect based on the material. And again, just to kind of drive the point home is that it not only works on normal incidence as other metamaterials would, but as we increase the angle incidence, you get a deflection in the transmitted beam that's consistent with the same index of about -2. And here's probably the most condensed data set where I show you that everything's actually within index of about -2. I mean, within numerical error in your FTD simulations. Another cool thing is that, okay, there's been this craze since the beginning of metamaterials. People said negative index is so cool, and I showed you images, and they do look cool. But there's more to it than that, right? So what I did right here, I showed you that there was negative index if I excite, for example, at 43. So I'm actually to the left of this 0 point. But what happens if I actually excite at the k equals 0 point, or slightly above that, where n is equal to 1, right? So that's also very interesting. Now you can imagine materials that are impedance matched, but conductive, which could be very interesting for technological applications. Here I'm showing you that n equals 0. It's kind of hard to see. Maybe I should just do like a greater angle. But what this means is that no matter, if it follows Snell's law, it means that no matter what angle I come in at here, it's always going to come out normal to the surface, right? Because the output, the index inside is 0. Similarly, you can get n equals to 1. This is the one that my advisor is really excited about because I don't have them here, but if I actually vary this from normal incidence to about 30 degrees, it just goes straight through, regardless of the angle of incidence. So you can imagine that could be very, very interesting, like for display technology and so forth. And actually, Harry's really big on solar cells, and what I want to tell them is that these still have huge losses in them because they're metal, but that's really bad. And then here, we can access negative indices, 0 index, n equals 1 index, which is really cool, and also very high indices. This is probably the one that I'm least excited about, but it could be interesting because you can actually do multiplexing. You can send in a beam, and you can actually spread it out and do different things, for example, for on-chip application. Okay, I have, a few more minutes. telling you that this is not just make-believe, we're actually fabricating these. And the fabrication is about a week away right now. And it's kind of funny because in PowerPoint, this looks like it took me as many clicks as it did to fabricate it. It just, things that I'm doing, I use FIG, rectify, and etching. I can go into detail about this later. But, this actually took about 4 months to try, as you guys know, research doesn't work that well. But what we actually want to do in the end, I'm sorry, let me just show you. So I told you it was coaxial rings. These are like coaxial rings, which we're able to fabricate with large-scale uniformity. We actually are able to get very small feature sizes, which is almost pushing the limits of E-beam lithography in this case. And we're able to get very straight sidewalls within 200 nanometers. I didn't mention, but we actually don't need that thick a material because the index is only about, and we're working at 400 nanometers. We only need about a 200 nanometer thick layer for it to operate. And this is the most recent. This is like hot off the press. I was just doing this yesterday, where I was able to infill the metal, right? That's one of the big challenges because I don't know if you guys have done much fab, but if you actually try to infill small channels that are only like 50 nanometers wide, what ends up happening is you just clog the top of this thing into empty. So we actually ended up using an electroplating technique, and now we're able to get this done. And we should be able. So the next step would be to cut a wedge of this material and then do the exact same experiment that by measuring the angle of incidence and the position of the refracted beam, we should be able to back out the index of the material. This is just a schematic of what we think it will work. Let me just leave you with, so negative index is cool and it's hot, right? At least it was 10 years ago. But right now, another interesting part is that, we focus, if you think about, positive epsilon and mu, most of the stuff we work with lies along this line, right? We don't really go above, high mu, low mu, or especially within this range, it actually becomes very interesting. What can we actually attain by this? So without going into too much detail, because Maxwell's equations are covariant, we can actually transform, for example, Cartesian to cylindrical to spherical, and they maintain the same properties, right? Well, there's other crazy things we can do, like for example, we can do a transformation that allows us to maybe make a hole that's in the center and just make it open, right? So now that means that if you excite, whereas a propagating light ray would go right through it, now you actually are able to open that and it would go around this open space, right? The way to think about that is that instead of elongating space, it is equivalent to changing the index of that space, right? So it actually accumulates a different phase as it propagates. So like in this case, for example, if it was going to propagate with some phase here, if I wanted to go around this circle, it would actually have a different refractive index such that when it gets from point A to B, it would have the same phase as from A to B, right? And the interesting thing is that you can actually, instead of transforming the coordinate system, you can actually transform the permittivity system. So they're equivalent, and if Professor Schramm was here, who does relativity and so forth, he could attest that this is true, okay? In 2006, Sir John Pendry and David Smith at Duke University found one of these such transformation systems. Again, we were working with negative index, now they just work with any index, And what they found is that if they find an index in the z direction, so right now what they excited was with a plane wave with an E field coming out of the board and the H field is end plane. So if the EZ is constant, and then you're able to modify the radial permeability from 0 to 0.3, you are able to actually open up a hole in space, so to speak. And that's interesting, right? Because what that means is you can actually create a cloak for space, right? And what they did here was that I had a couple movies, but you can imagine that if you have a phase function moving forward, without any circle being there, this is exactly the way they would behave, right? But if you actually tune the index parameters inside of this donut, such that they follow this recipe, you're going to find that you're actually able to send face fronts that you can see here, the face front, I guess here was like the maximum value. And you can actually have zero scattering as you propagate to the other side, right? Which is really cool. I mean, kind of science fiction because this is only a two-dimensional system. And of course, the big limitation is that these metamaterials, at least this was done with split ring resonators, they are very dependent on angle incidence. So when he did the experiment, there was a little bit more scattering, but the point is that in theory, you should be able to design something that is able to probe something inside here. Like for example, I mean, if you put like a copper sphere here, it wouldn't scatter, which is really, really impressive, right? In my perspective. So with that in mind, I just wanted to give you a taste of the field of metamaterials and cosmonics. And if I could summarize it one way, it would be that electromagnetic metamaterials allow us to access like index parameters not accessible in nature. Not to say that they don't exist. I mean, butterflies have photonic crystals in their wings, and it gives you these very interesting colors. But I'm talking about everyday type of materials that are not super magnetic, or superconducting for that matter. But they can give you very interesting behavior, like I showed you as negative index, cloaking. This is the vision. The one Smith showed was for 2 dimensions, but you can imagine getting carried away and kind of doing like a 3-dimensional. Now you can do like real Star Trek, cloaking in there. I didn't talk too much about this, but you can actually have a perfect lens. A perfect, like a lens is limited by the K vectors transverse to the propagation direction, right? It actually just decay because of the dynamics of the K vector. But because negative index allows you to have a negative component, you actually enhance those fields, and you can actually have sub-wavelength images transfer across the system from one point to another. The big critique about this is like, if I can just put a point from there to there, why can't I just measure it there, right? But still, it's still kind of interesting. I think the main thing here is that we could actually not only transfer it, but make it, magnify it. Then you can bring conventional optics to bring that into out of the diffraction limit. And I guess my contribution in all this work was that I showed you that through using plasmonics, we were able to kind of break the wavelength barrier and go into the visible wavelengths. But most important for you guys sitting out there right now and thinking of what to do next, realize that this is just a starting field. Like similar to back in the day, in the early 1900s, when there was a lot of physics that was being born, and people didn't know where it was going, and all the standard textbook stuff. There's a lot of stuff now that is just being investigated, and 20 years from now, it will be textbook. All of you have the opportunity to take part in that. So with that, I'll take your questions.
Questions for Stan? I have a question for you. That I've always wondered why Hendry had 2 rings that were sort of counterbalanced each other. So what was the logic?
So you actually are able to have more different capacitance between the 2 rings.
Okay.
So in addition to having the capacitance, so you actually are able to have a stronger resonance.
Sure.
A single one should do it. Yeah.
So I kind of lost track during the talk. Which part of this is theory and which part is experiment?
Everything that I showed for the split ring resonators, that I presented more the theory aspect, but all that was shown experimentally. Negative refraction, the cloak, all that's been experimentally demonstrated. The plasmonics has been, I'm sorry about this, it's a little bit vague. But the superlensing, this has been shown using plasmonic systems. The most recent one has been this one, and I showed you the fabrication that's going on. And we're actually going next month with our collaborators to actually do the final measurements of the device. Yes, sorry about that.
For the cloaking, does that mean like you would be able to stop like physical
explain that correctly, but if I, the reason why I'm able to see something standing in front of me is because light, comes in and scatters and, hits my eyes. But if you're actually able to have that light not scatter, meaning that if you can tune the index around that object such that it just goes around it, then I wouldn't be able to see it. So it's not that objects can penetrate it, it means that electromagnetic radiation goes right through it without the scattering. So a simplified way to say it would be that you reduce or you eliminate scattering entirely.
And that didn't require negative index for refraction.
Exactly right. Yeah. So I initially had that at the beginning, but just to be consistent, here you can see that the permittivity is just greater than 1. The only thing that was varied was the permeability, which went from 0 to 0.3, which again is one of those things that you always assume it's 1, but if you actually tune, actually it does another hot field, everything going from 0 to 1